So we are going to start with a homework question.
Let's do 15.
We're recording
16.
now.
Let's do 16.
What problem is it?
16.
Number 16? So we're going to go through number 16 on the homework. So my numbers might just be different than yours, but it's going to ask me to do the exact same thing. It says an airplane flies horizontally from east to west at 314 miles per hour relative to the air. If it flies in a steady 48 mile per hour wind that blows horizontally towards the southwest, which is 45 degrees south of west, find the speed and direction of the airplane relative to the ground. So we've got an airplane speed and direction, we've got a wind speed and direction, and we want to know when these two things get combined, what the actual path of the airplane is going to end up being. And they've already drawn the pictures for you. That's the first thing they're asking, is which picture is correct. So let me open up. So if we've got an airplane going from east to west, that vector is going to point in the direction of motion. And then the wind is blowing 45 degrees south of west. So the picture options they give us look like they're doing the polygon method. Because they're taking one vector and they're putting its initial point where the other point, or where the other vector ends. So we want to know which one of these. Assume that vector W gives the direction and speed of the wind. The vector V sub P gives the direction and speed of the airplane relative the air. And the vector V gives the direction and speed of the airplane relative to the ground. Place the vectors in a coordinate system and choose the correct diagram below. So where the airplane leaves off, we're going to start our wind. Our wind is pushing southwest, so 45 degrees south of west. That's down in quadrant 3. So we point our vector down in the direction of quadrant 3. And that is our wind. And then polygon method says the sum is going to be the vector that connects the very beginning to the very ending. So the actual path of the plane should be that one. But we've got a couple pictures that look like that. This one kind of looks like that, but they're doing it with parallelogram method. If you look at A and B, the triangles are exactly the same, but there is a difference in A and B. And it's hard to see the labeling exactly. So they said they want W to be the wind, they want V sub P to be the airplane, and they want V to be the actual direction the plane ends up going in relation to the ground. So if you look at A, they've labeled the big long one W, which is not correct. We want our airplane going straight west, and then we want our wind going southwest to result in that ground speed and direction. So C is similar, But C is using the parallelogram method instead of the polygon method. The problem with C, and this is hard to see from, I don't know if I can write on my screen or not. I'm gonna try to. No. All right, if you were to try to finish drawing out that parallelogram for C, I think you would find that the V vector they drew in the middle is not long enough. Because W is gonna have a parallel side over here that's gonna look exactly the same. And the V should go all the way out to it. They've stopped vector V at the same exact position they stopped V of P. And that's, if we were to, we could do this with the parallelogram method, but if we did, our diagonal would not look the same as what they've just drawn the diagonal to be. So it's possible C could work, but it is incorrect because V is not long enough. And then in D, they've got the plane pointing in the wrong direction. So our answer is going to be B. I was going to say, watch it come up incorrect. That'd be hilarious. The speed of the airplane is approximately. So speed is magnitude of velocity. So for each of these, we've got a magnitude and a direction. And we want to put those directions in standard form as a standard angle with respect to the positive x-axis. So the plane moving due west would be how many degrees? 180. And then the wind moving southwest would be what? Now, I wouldn't use 45. We want to compare it back to the positive x-axis. If we used 45, we'd get the same numbers, but our signs might not be right. Because when things point in quadrant 3, all the signs should be negative. And 45 technically is in quadrant 1 where everything's positive. So we'd get the exact same numbers, but we'd get the wrong signs. So we want to do it from 0, and 45 south of west goes 45 past 180, which is 225. So we want to take both of those vectors and break them down into components. Once they're in components, we can add them back together and turn it back into a magnitude and a direction. So 314 and 48. So we've got our, oh, this is ugly, conversion formulas that will change these guys to components. Make sure your calculator is in degree mode. And then once they're broken down into components, we can combine like components. So we can add those x components together. We could add the y components together. So I like to plug these straight into the calculator just like that. That way it doesn't do any extra rounding. So I'm just going to ask the calculator, what is 314 cosine of 180 plus 48 cosine of 225? And then go back and change them to signs. This is going to give us components for our answer, components for regular V, which still is not the answer that MyLabs Plus is looking for. MyLabs Plus wants magnitude and direction. So once we have these components, we can go back to magnitude and direction for our final answer. So R sub x, if we do 314 cosine 180, but just make sure you're in degree mode, plus 48 cosine 225, because both of those are x components. Both of those are pointing horizontally. I got negative 347.94. And then the exact same thing for the y's, 314 sine 180 plus 48 sine 225. We can add them together because They're both y components. They're both pointing vertically. I get negative 33.94. So both components are negative. That's because the direction of the plane is going to be into quadrant 3. And in quadrant 3, our coordinates are both negative. You need to be careful when you do your angle, because your angle is not going to come out as a quadrant 3 angle. So we actually want magnitude and direction. And remember, you can think of r sub x and r sub y as the legs of your right triangle. The actual magnitude is the hypotenuse. So changing your components back to a magnitude is just the Pythagorean theorem. So they wanted us to call it v. So this is the speed of the plane. And they want the answer rounded to the nearest hundredth as needed. Be careful, because both of those negatives, when you square them, are going to turn to positives. Nothing actually is going to get subtracted. You should not end up with a negative number under your square root.
349.59.
Yep. 349.59. And then our angle, which goes on top, the y or the x. The angle is tan inverse, because we've got legs. We do the y on the top, the x on the bottom. Yep. But our calculator does not always give us the answer we want back when we do inverse trig. Sometimes we have to take that angle and move it into the correct quadrant. We know, because our components are both negative, that our answer should be in quadrant 3. And depending on how they want us to answer this question, we might have to adjust what the calculator tells us. So tan inverse of our r sub y was the negative 33.94. And our r sub x was the negative 347.94. That should give you a quadrant 1 angle. But what the calculator says is not necessarily going to be my answer, but it is helpful. My calculator says 5.57. But I'm going to go back and see how they want it answered. Because they might just say 5.57 degrees south of west, and then we can just use it. If they want it back in relation to the positive x-axis, then we would have to add 180 to it. So 349.59. And they want us to select a unit, and the unit is going to be exactly the same as the units that they give us in the problem. So the plane's airspeed is in miles per hour, the wind is in miles per hour, so the plane's ground speed is also going to be in miles per hour. And then the direction of the airplane, I'm not going to type a number in yet. They do want you to attach a direction to it, so we don't have to change the 5.57 because it's 5.57 south of west. South of west is what puts us in quadrant 3, so we don't have to add the 180 to put us in quadrant 3. So just using our conversion formulas, almost always you end up using both sets of conversion formulas. You've got to take a magnitude and a direction and turn it into components so that you can actually work with it. And then they usually want the answer back as a magnitude and a direction. So once you get a final answer in component form, you then have to convert it back. So almost always you're going to be if you have to use conversions, you're going to be using both sets of conversions. You're going to convert it to components in order to do the math, and then you're going to convert it back to answer. Other ones in the homework? No? Okay. So everybody cross your fingers. I'm gonna fold back my keyboard. It was messing up last week when I rotated it. I don't know if it still considers the keyboard tucked away to be tablet mode or not. I saw that. That might be our demise. The end of the video. We shall see. Yes. All right, so in class on Thursday, we started talking about 11.2. And we pretty much just introduced the 3 coordinate system. Coordinate space where we use coordinates X, Y, Z. And then we changed all of our formulas from 2-dimensional to 3-dimensional. There's a pattern in them, and all we have to do is extend that pattern out to include either the Z coordinate or the third component in the vector if it was a vector formula, or something like that. So most of the formulas should be fairly familiar if you know them from 2 dimensions. They're really not going to change at all when we go to 3 dimensions. They just have to include the third dimension in there, following the same pattern that you already see. We did not get a chance to do any examples, though, from 11.2. So we set our 2-dimensional formulas. Easily extend into 3 dimensions. We just have to include the third coordinate or the third component and follow the same pattern that we see with the first 2.
Yeah.
So you should all have a list of formulas for 3-dimensional stuff. And I'm just going to have you do some examples. The first one we're going to do is we're going to find the equation of the sphere that has a diameter with endpoints to -5, 1 and 6, 1, 9. How are we going to answer this question? Not what are the steps, but what is your final answer going to look like? What are we going to be giving as a final answer? An equation for a sphere. Our final answer is going to be the equation for a sphere. So to start this, we should look back and see what the equation for a sphere is and what sort of information we need in order to write out the equation for a sphere. So this is one of the things we had in our chart on Thursday. We extended out the equation for a circle and just included the z component to make it a sphere. So that formula, hopefully, you have as x minus, what did we call them, a, b, and c? Mm-hmm. X minus a squared plus y minus b squared plus z minus c squared equals r squared. That was the equation for the sphere that we talked about last week. What did ABC represent? Did we say? So if this was just a two-dimensional circle,
Was it R squared or R cubed?
it's r squared. It is r squared. We talked about it possibly being r cubed, but then we had a little discussion of why it couldn't be r cubed, but I don't think I wrote anything on the board for it. So you might not have notes as to why. So we don't remember what ABC represents? You remember in
To
two
change the
dimensions?
origin. To change
Yes.
the origin.
Yes, it is a movement from the origin. That's the algebra concept. When you subtract inside of a function, it moves the function to a different spot. So the minus a, the minus b, the minus c, the a coordinate is going to move the center of the circle from 0 to a. The b coordinate is going to move the center of the circle in the y direction from 0 to b. So the a, the b, the c, that is the center of our circle. Without those numbers, it would just say x squared plus y squared plus z squared equals r squared, and we would say that's a sphere centered at the origin. If there's nothing being subtracted, then it's at the origin. The subtractions inside, back from algebra class, if you subtract either inside of the function or outside of the function, it's going to do a horizontal or a vertical shift. So that's exactly what it does. It shifts the origin of the circle. So ABC is the center of the circle. When you are subtracting, it goes the opposite direction of what you would, if it's inside of the function. If there is a function operation outside of it, then you do the opposite of what it says on the variable that it says. So x minus a really means the origin is going to have an x coordinate of positive a. So minus a, you would think minus is going to move me left. It doesn't. It moves you right. And the B and the C, because they're inside of a function operation attached to their appropriate variable, they're opposite as well.
So if they're not attached, it's not.
Correct. If it's outside of the square, then it's a movement on our output value. And it does exactly what it says. And then R is what? R is the radius. So how can we use the information we were given in this problem to find the center and the radius? We were given two endpoints on a diameter. What is a diameter of a circle or a sphere? Anybody know what a diameter is? No.
Double the radius.
It is double the radius, yes.
The distance between two endpoints.
It's the distance all the way across your circle. The diameter also always goes through the center. So half of it will go from the edge to the center, and then the other half will go from the center to the edge. So that means the center is exactly halfway in between those 2 points. The center of our circle will be exactly halfway in between those 2 points. So we can use our midpoint formula to find the center of our circle. So that's one of the first things we need to do. And that's one of the pieces of information that we need to answer this question. So we did have a midpoint formula in our chart last week. Midpoint really is just averaging the coordinates. Add them together, divide by 2. Your answer is still a point on the graph, so it's still going to be written as a point. Your x's, your y's, your z's stay separated. We just want to know what is halfway in between 2 and 6. What's halfway in between 1 and -5? What's halfway in between 9 and 1? So to do that, we add them together and divide by 2. So to calculate our center, we've got the 2 points. We've got the x2 and the x1, the y2, the y1, the z2, the z1. Really doesn't matter which one you label as point 2 and point 1 because we're just going to be adding them together. So we've got 2 plus 6 over 2 for my x coordinate. -5 plus 1 over 2 for my y coordinate. And then 1 plus 9 over 2 for my z coordinate. Those are the x's, the y's, the z's that we were given for the diameter. And we want to know what's halfway in between them. So what do we get for our center?
4 -2.
This is our ABC. This is 3 of the 4 unknown numbers in that formula. The only other piece we need is the R, the radius. And what is the radius of a circle or the radius of a sphere? It's half the diameter. I'm not going to suggest you solve it that way, though. In case it comes out to be an irrational number, you might get confused on how to half an irrational number. We're not going to do mid. We're going to use what we got from the midpoint formula because what is radius? Just like in words, what's the definition of radius? Yes, it's a line and it goes from the center out to the edge. Now that we have the center, We just need to know what the distance is between the center and one of our edge points. Distance formula. We're going to do distance formula. And there is subtraction in there.
So you just add another, it's like x2 minus x1 squared plus y2 minus, is that up here?
It's in our chart from last week. Do we have distance formula?
No. So we just add another z1,
Did we have?
z2 minus z1 squared.
I thought we had something similar to it.
We have the component formula.
Yeah.
Doesn't have
Yeah.
square root.
So the distance formula in 3 dimensions, you're just going to throw in a z2 minus z1 squared in your square root right along with your x's and your y's. So our distance formula so that's the normal distance formula in 2 dimensions. So to extend it out to 3 dimensions, we're just going to throw it exact same thing we see with the x's and the y's. We're going to do the same thing with the z's in there. And we want to know the radius, which is the distance from the center to the edge. So in this formula, we're going to do 4, -2, 5, and you can take either one of those edge points, and you should get the same answer either way. So it's really up to you. I'm going to do 619. Feel free to do the other one and we can compare and show that we have the same answer if you want to. If we can find the distance between those 2 points, then we have the radius of our sphere and we've got everything we need to set up our equation. It doesn't matter because if we change the order of the subtraction, the answer is just going to change from positive to negative. But then what other operation are we doing to it? Squaring it. So whether we get -3 or +3, what's the square for both of them? +9. So it really doesn't matter which one is 0.2 and which one is 0.1. You should be consistent though. So if I'm going to use 4 as my x2, then I need to use -2 as my y2 and 5 as my z2. So if we plug our points in, I'm going to do 6 minus 4 squared, 1 minus -2 squared, and 9 minus 5 squared. If you did the other point, the subtraction step's going to look different, but after you do the subtractions in the squares, you should have 4 and 9 and 16 as the squares that you're adding together. That should still be the same. Because the x2 minus x1 is just the individual x distance. And that center was supposed to be equidistant from both sides. So it doesn't matter which direction we go, which endpoint we use. After we subtract and square, it should be 4 either way. So we get radical 29 for the radius. So that's everything we need to set up our answer. We've got our center, we've got our radius. Now we just need to write out the proper format for the equation of a sphere. So we had it up here earlier. We said it was x minus a squared plus y minus b squared plus z minus c squared equals r squared. We know the a, the b, the c, the r. The x, the y, the z are going to stay. We're not being asked to solve anything. We're being asked to write an equation. So if I asked you to write an equation of a line, What's slope-intercept form for equation of a line? Y equals mx plus b. But you leave the x and the y in there, you just find the m and b values and plug them in. But the x and the y stay, because it's an equation. That equation represents lots of points that work. And the same thing is true here. Leave your x, y, z alone. Those are staying in the equation. What we're replacing are a, b, c, and r. So our center was 4, negative 2, 5. So x minus 4 squared plus y minus negative 2 squared plus z minus 5 squared equals radical 29 squared. And we do need to clean this up a little bit. So there's two things that we can do to fix it. We don't want to FOIL any of it out. Don't do that. Y plus 2, yep. Minus a negative is a plus. And what was the other one? Right, just a regular 29. Square and square root cancel. So I tricked you into using like 4 of our formulas in one problem. So if it took a while, it's okay. We really did like 4 problems. We used midpoint formula, we used distance formula, and we used our sphere formula. We also got a good little review of transformations, thanks to Adam. Minusing inside just shifts our graph around. We could have easily been asked to work the same kind of problem back in algebra class, except it just wouldn't have the z's in it. It would say find the equation for the circle, which with a diameter that has endpoints, and they would be 2 coordinates, just x's and y's. And we could do midpoint and distance and set up the equation for the circle. So the only thing different here is that we've got a 3rd coordinate. But everything we do with the z's just follows along with the exact same pattern of what we did with the x's and the y's. Questions so far? Is it break time? I am still recording. Yes, I know I'm being quiet. All right. We're going to take a break. 10-minute break. I need to figure out how.
wasn't watching. I don't know how much do you want, how much is, like, the one we got was $750 at, Dunham's, but we got it like $200 cheaper.
My kid's got a 22, AR style 22 for Christmas.
Yeah, that one.
My dad got it from
Iron
a law
sight.
enforcement place, so it's a lot cheaper.
Iron sight.
Yeah, pop up.
All right, next example. We're going to find a unit vector that has the same direction as PQ if P is negative 307 and Q is 5 negative 41.
Iron sight, so either that or there. So, there. Sight.
So ultimately, what are we going to answer? How do we know we're done? What are we going to circle? Almost, not a direction, not a degree. Find a unit vector. So there's a couple things we need to do to get to that point. Our ultimate goal is to have a unit vector. Did they give us a vector? Actually explicitly hand us a vector? No. They gave us information that we could use to create a vector. So that's the first thing we need to do. We need to create the vector. And then once we have the vector, then we can turn it into a unit vector. So we did have this formula in our little chart on Thursday. Remember, you always go from the terminal point and then subtract the initial point. These components for your vector not only represent the ending point when the vector's in standard position, but they also represent change, how much the values changed from the beginning to the ending. So if the value got bigger, then we need to make sure to do the bigger number minus the smaller number so the answer comes out positive. That means a positive change. The value went up, it got bigger. So always do the ending minus the beginning. If that comes out negative, that means the ending was smaller and the value went down. So you're always doing your Q's minus your P's for vector PQ. There's one tricky one in the homework that asked you, it said, here's point P, here's point Q, set up vector QP. So just be careful with that. That means Q is the initial, P is the terminal, and you're going to be doing the P minus the Q to get the component form. So they just gave us coordinates in space. We need to turn it into a vector as our first step. So terminal point minus initial point. So we're going to do 5 minus negative 3. That'll tell us how our x coordinate changed. Negative 4 minus 0 will tell us how our y coordinate changed. And then 1 minus 7 tells us how our z coordinate changed. So now we have a vector. We were asked for a unit vector. That thing is definitely not 1 unit long with components 8, 4, and 6. 8, negative 4, negative 6. That thing's going to be way bigger than 1 unit long. If it goes out 8 units in the x direction, 4 units in the y direction, 6 units in the z direction. So the second part of the problem is to now take that vector and shrink it down to a unit vector. How do we do that? Divide by the magnitude. Yep, so we need to know what the magnitude for PQ is. And the formula we said was going to be v1 squared plus v2 squared plus v3 squared. If our vector is in component form, v1, v2, v3 are our components. It's just like distance formula. This pattern looks just like distance formula, except the subtraction is missing. Do you know why?
Because it's.
You're subtracting zeros, right? If it's in component form, that means the initial point is 0, 0, 0. So minusing zeros don't do anything. So we just don't even use it in the formula. So we've got 8 squared plus negative 4 squared plus negative 6 squared. Which does simplify. We get square root 116. You guys know the fast way to simplify this on your calculator? Have I told you? So if you're not sure if a radical is going to simplify or not, in your calculator, you can do y1 equals 116 divided by x squared. Since it's a square root, it's only going to simplify if we can pull out perfect squares. So what we're doing here is we're checking to see if 116 has any perfect squares, perfect square factors. So we're dividing it by x squared, and then we're going to look at the table. If you see any whole number x, y coordinates in your table, then that's how it's going to simplify. The x is what comes out, and the y is what stays in. Two, and what's next to the 2?
29.
Okay. If you look farther down, are there any other whole number pairs? Nope. We don't want the decimals. If we wanted a decimal, then we would just ask the calculator what square root 116 is and use a decimal there. So your calculator does say that this can be written as 2 radical 29. The reason the first number comes in front is because if I pull an x squared out of 116, it's still under the square root. The square and the square root cancel, and it's really just an x that comes out, not the whole x squared. So 116 is equal to 4 times 29. And we can do the square root of 4, that's 2. We can't do the square root of 29, so that just stays in. So it's kind of a fast way to do it on your calculator, especially when the numbers get really large or weird or just unfamiliar. So to turn our vector into a unit vector, we're going to divide by the magnitude. Originally it was 8, negative 4, negative 6. Dividing by a scalar is exactly the same as multiplying by a scalar. We just distribute it into each piece. And there's a reason I wanted to simplify that square root. All of my numbers, all my components in my vector are even numbers, and we were able to pull a 2 out of our square root, and there's going to be some simplifying that we can do. So I'm not going to do it on my first step, but we get 8 over 2 radical 29, negative 4 over 2 radical 29, negative 6 over 2 radical 29. And a lot of that stuff's going to simplify. Now, when it comes time to take our test, I don't care if you rationalize or not. You can leave it as 4 over radical 29. That's perfectly fine with me. In MyLabs Plus, they might make you rationalize it. So to rationalize, we're just going to move that root to the top. And cancel off the root symbol in the bottom. And you should check to see if anything new simplifies, but it doesn't. I think 29 is prime. It's not going to be able to do anything with it. That's our unit vector. So first we had to make our vector, we had to do our distance formula, and we had to do a unit vector formula. So again, we had to use 3 formulas on one problem. We talked about parallel vectors with 2 coordinates in the 2-dimensional system.
What did you just change the sign?
Huh?
Didn't you just change the sign?
You could just change the sign. That would give you a parallel vector because that's going to move the arrow from one end to the other, which is like a 180-degree turn. But if you actually draw them, they still look like parallel lines. So V and W are parallel vectors. If, look back in your 11.1 notes and see what we said there between the relationship between V and W. We might not have said V and W, but we might have said U and V.
What are they? They have the same magnitude, the same role, something.
That's equivalent vectors. Equivalent vectors will have same magnitude, same direction. For this one, we just want them to be parallel. Just same direction. And what kind of vector do we use for direction? Unit vectors. We don't care about the magnitude at all. All we care is that the directions are the same. So if the magnitude can really be anything, we just have to worry about the direction. What's ultimately going to happen is if we change both of these vectors down to unit vectors, they're going to match if they're parallel. The originals will just be a different scalar of that unit vector. So V might be 4 times the unit vector, where W is like -2 times the unit vector. But both of them shrunk down to a unit vector are going to match if they're parallel. So what that means in relation to one another, if V and W are parallel vectors, then one of them is just a scalar multiple of the other. One vector is just a scalar multiple of the other. That means they have the exact same direction, they just have different magnitudes. Because all a scalar does is change our magnitude. Now, nothing in that formula says anything about it has to be 2 components, it has to be 3 components. So we're not going to do anything differently with the space vectors than we did with the plane vectors. All right, so every single one of us is going to give an example of a vector that's parallel to that. So we've got Joa, Eason, Arturo, Tyler, Adam, and Kirby.
Why'd you put AT?
Atom.
I don't know. I figured
I have no idea. I'm sorry. A sub D. We've got A sub R and A sub D.
I got one.
All right, Arturo's first.
-2, 1, -5.
Perfect. Perfect.
$306.
No.
6,
Nope.
7, 5.
One vector must be a scalar multiple of the other.
Oh, okay.
4, -2.
Joa was louder.
Recording.
I heard Joa say 4, -2. What?
6, -3, 15.
Eason says 6, -315. All right, I think we've got the hang of it, right?
100, -50, 250.
Adam says 100,
1/2.
-50. hold on. 250.
2,000. Infinity, -1 infinity.
20, -10, 50.
So you see what they're doing, Kirby?
Yeah.
Okay.
40, -40.
Nope.
I mean, not -40.
What'd you multiply to go from 2 to 40?
-1. Wouldn't be negative.
So -20
and 100.
and 100. Any vector that is a scalar multiple of the original will be parallel to it, no matter what crazy number you use. So Arturo used a negative. He was the only one that used a negative, and negatives are perfectly hacks. No, facts. Negatives are fair game because if you actually look at the picture of those two vectors, they still look like parallel lines. We don't really care what side the arrow is on. So all those vectors are parallel. We had a little too much fun with that. Good, that makes me happy.
Please. Or snap dog that don't stop.
All right, 2 more things real quick to finish up section 2, and then we're going to talk about dot product for 5 minutes because it's really easy. Just the calculation of dot product. And then later we'll actually go through what some of the applications of dot product are. Just so you know how to do the calculation, even though probably most of you already do from physics. So good, it'll go fast.
Will you refresh?
Yes, so we'll still go over it.
Add off.
I'm going to change back to black. So this is something you may have not heard before because you've never, maybe in physics you did, but in math classes we've never really done anything in 3-dimensional space. So collinear points are points that all fall along the same line, or that all lie on the same line. We are going to use vectors to prove collinear points. So for example, if we had R, S, and T, and I wanted to prove that those 3 points were all along the same line, I do my best. There's probably a drawing tool on here where I could draw a perfectly straight line.
I think you must shake it. I said I don't trust those points, they're all lying.
They're all lying.
They're all the same line, they're lying.
All right, let's play with our tools. I get it.
It's a good one, right?
It was amazing, Eason.
It's kind of close.
Yeah, plus one.
Yeah, no, I don't think so.
It's
S
close.
is kind of off.
Was it better? It's better than my last one, right?
That was pretty bad, yeah.
Yeah.
That's a good point.
So what we can do here is make the point bigger. This is the trick. This is the trick. You make the point bigger.
That's
It's cheating.
Now it's a circle. I gotta grab this one. Okay.
All right, so this is what we're going to do. We're going to be able to prove that these points all are on the same line. All we have to do is form two vectors. Form two vectors. Use all 3 points and just form two vectors. Now, some of us might form different vectors, and that's perfectly fine. We'll all come to the same conclusion. So one option is we can create vector RS. What's another vector we can make? Anything.
ST.
We can also make ST. If we move those vectors around,
SRT.
so here's RS, here's ST, how would you describe the relationship between those two vectors? They are parallel. Any vector that you can make with those 3 points is going to be parallel to every other vector. So you also could have made RT. You also could have made SR. But you have to make sure all 3 points get used.
SRT.
You could have made, we can't make SRT. We also could have made, oh, I'm running out of colors. We could make TR. We could make TS. Do I have one more? So we can go end to end, or we can break it up. There's 1, 2, 3, 4, there's 6 different vectors there. All we have to do is show that 2 of them are parallel and use all 3 points. And we'll have just proven that all 3 of those points have to be on the same line. That's the only way that those 3 points can form parallel vectors, is they all must be on the same line. All right, so are the points R, which is 0, -2, -5, S, which is 3, 4, 4, and T, which is 2, 2, 1, collinear. We want to know if those are collinear. We've got to make 2 vectors. And between those 2 vectors, all 3 points have to get used. So somebody tell me one of the vectors we're going to make.
RS.
RS? Sounds good. My first, no, we can't. SR is the only one we can't do. Because now that we have chosen R and S for vector 1, T has to get used in the second vector. Second one has to have T in it. We can't do TT.
ST. ST.
RS and ST.
D. Or T.
So remember, you're going to do ending minus beginning. So for RS, we're going to do the S coordinates minus the R coordinates. So 3 minus 0 is 3. 4 minus -2 is 6. 4 minus -5 is 9. So RS is the vector with components 3, 6, 9. ST, those are going to be the T's minus the S's. So 2 minus 3 is -1. 2 minus 4 is -2. 1 minus 4 is -3. It looks good. Some of these you can't really tell just by looking at them because they've got some crazy fractions and such in them. So I'm going to show you a way that you'll know for absolute certain that these are multiples of one another. We are going to create fractions between each of the components. So I'm going to create that fraction and see what value it gives me, and I should get the exact same value when I create it between the y's and the z's. So 3 over -1, oh, that's not a highlighter. So 3 over -1 is -3. 6 over -2 is -3. 9 over -3 is -3. This means that RS is -3 times ST. All of the RS values are exactly -3 times the ST values. So one vector is just a scalar multiple of the other. That means the two vectors are parallel. That means the points are collinear. If any one of these were to come out to be a different number than -3, then we would say no. So RS and ST are parallel. Which means R, S, and T are collinear points. So component form has a couple of different meanings. One of them we said is the vector that goes from 0, 0, 0 to V1, V2, V3. But if you look back at the formula on how we get component form, if you're given 2 points and you're asked to put it into component form, how would we get the x component if we were given 2 x coordinates? X2 minus x1. Subtraction represents change. It's describing how the x value is changing from the beginning to the ending. So since this formula has subtraction in it, we can also use these components just to represent change, how the points are changing as we move along the vector, or how the coordinates are changing, how the components are changing. So there's two ways you can think of these component forms. You can think of them as the end point of the vector that starts at 0, 0, 0. You could also think of them as describing change on the vector, especially if the vector is describing the direction of a line that goes on forever. Then technically we don't stop at v1, v2, v3. If we're using it for its direction and we want to go forever, we can go even farther than just v1, v2, v3. So something I want you to think about for just a second with this in mind. Instead of thinking of it as an endpoint, think of it more as change. If we know that the component form of PQ is 3, -2, 1, and the initial point P is at 5, 2, -3. Find Q. We could use a formula for this, but think of it more as what does component form mean, and what information were we given, and what are we asking for? So if you think about component form as meaning change, how the coordinates change, what this is telling me is that as I move along the vector, the x coordinate is going to increase by 3, the y coordinate is going to decrease by 2, the z coordinate is going to increase by 1. So you can think of those numbers not just as endpoints, but as amounts of change. So if we slid this vector out of standard position and we moved it so that P was at 5, 2, -3, we want to figure out what Q would be. Think of those components as representing change from beginning to end, from initial to terminal. So on this vector, what x value are we starting at? On vector PQ, what's the x value that we start at? We're starting at 5. We're starting at P, which is 5. They want us to be at 5. And then how does the vector say the x coordinate is going to change from beginning to ending? It's going to go up 3. So to get the ending point, you just do your starting point and then include your change into it, and it will give you your ending point. What y coordinate are we starting at? 2. And the component form says as we move along this vector, our y coordinate is going to go down by 2. And then the z coordinate is -3. The component of the vector is +1. That means as we move along this vector, the z coordinate is going to increase by 1. So Q should be 8, 0, -2. So we also think of those components as representing change, not just an endpoint of a standard position vector, but we could also think of them as representing change. Change from the beginning to the ending. All right, so what I want you guys to try, be really careful about what you're given and what you're being asked to find. Vector PQ is -4, 2, 3. Those are our components. If Q is 5, 2, -7, find P. What's the reverse? What operation did we use in the last example? No, we used addition. Do your starting point plus your change. Somebody already did that for us to get the Q. We need to undo it to get the P. We need to go backwards to the initial point on this vector. So this Q represents the change already included. So we want to take the change out to see where we started. So to go back to the initial point, we're going to subtract. So start at your Q position and subtract your change. So for the X's, we're starting at 5 and we're subtracting -4. What's that going to give us for an X coordinate? 9, which if you look, that means the X coordinate started at 9 and it ended at 5. That makes sense. That's a change of -4. The X coordinate went down 4. So you're doing your ending minus your change. So what do we do for the Y? We get 2 minus 2, which is 0. And -7 minus 3 is -10. So if those are the correct components and the correct terminal point, this vector should have started at 9, 0, -10. So if these components represent change, we've used rate of change in lots of other classes before this one. What are some other things that mean rate of change? Slope. You can think of these as the slopes in each of those individual directions. So along this vector, if you look at it with respect to the x-axis, it looks like it has a slope of -4. With respect to the y-axis, it looks like it has a slope of 2. So these are the slopes you're following to get from the starting to the ending. What else do we use in calculus for rate of change? Derivatives. So once we introduce functions into these problems, which we're going to do at the end of the chapter, we're going to have derivatives here as well. So we are going to do a tiny, tiny, tiny bit of 11.3. We're just going to talk about how to calculate dot product, and that's it. And then later we'll talk about applications for it, because there's lots of different stuff that you can do with it. So 11.3 is dot product. So all of you have seen this before, either 4 months ago or 4 days ago, because we use it in physics. Yes. Now, yeah, I said we use it in physics uses it. Whether Eason uses it or not, it might be a different story.
I remember
I remember the few. I don't really know.
The dot product is the easy one. The cross product is the difficult one. It's got a much more complicated formula.
Yeah, AY, BC minus AZ, BY. Plus AZ plus AZ.
Huh?
And then basically where you multiply.
We're going to multiply and we're going to add.
Multiplying the X's, the
So-
Y's, the Z's.
Yep. So in 11.1 and 11.2, we talked about addition, subtraction, and scalar multiplication. We haven't talked about multiplying a vector with another vector yet because it doesn't work the same way that it does with real numbers. So there's actually two ways to multiply vectors, and they both do something a little bit different. And the first one's called the dot product here in 11.3, and the second one's called the, we call it the cross product in calculus. Okay. And, yeah.
Cross product. This one's
Scalar product. And I was going to write that on the board or on our thingy. So this is also called the scalar product. And the reason it's also called the scalar product is because it's got an answer that's a scalar. When you do the dot product of two vectors, the answer is a scalar. And I'm going to jump straight to 3 dimensions because we know the pattern will be exactly the same. Doesn't matter whether we're working in 2 dimensions or 3 dimensions. If we've got vector V with components V1, V2, V3, and vector W, which has components W1, W2, W3, V dot W. So literally the dot product symbol is a dot. So I guess it's called dot product because of the symbol that it's used. It could also be called scalar product because the answer is a scalar. But dot product and scalar product are the same thing. So V dot W, to calculate a dot product between two vectors, you are going to multiply corresponding components. Just like when we added 2 vectors, we added corresponding components. When we subtracted corresponding components. So V sub 1 represents change in the x direction. W sub 1 represents change in the x direction. They're both moving in the same direction, so they can be combined. When everything's moving the same direction, we can combine them. Okay, so we're going to multiply corresponding components. So that's a product. V sub 1 times W sub 1. We're also going to multiply V sub 2 and W sub 2, and V sub 3 and W sub 3. So you're multiplying corresponding components and adding the products together. And your answer is not a vector, it's just a number. You just get a number answer back. This is multiplication and addition. We're going to find V dot W and W dot V. So V's got components 2, negative 4, 1. W's got components 5, negative 1 half 3. Will it be the same? That's what we're going to find out.
No. Yes.
We got some yeses and some nos.
Yes.
So let's check and see. And then I'll tell you why we got the answer that we got. Says in your book, yes. Let's see. So multiply corresponding components. So we're going to multiply our x components together. We're going to multiply our y components together. Yes, there's a fraction in this one. It's okay. multiply Z components together. That looks like 10 plus 2, because double negative, plus 3. Now, if I do W dot V, what's going to change? Just the order of what? The multiplication order. Multiplication is commutative, which means it doesn't matter what order you multiply in, you're still going to get the same answer. So if we do W dot V, that just means our W's are going to be written first and our V's are going to be written second. That doesn't change how the multiplication works out, though. Whoops, sorry. Still multiplies out the same. It's still 10 plus 2 plus 3. So V dot W is the same exact thing as W dot V. And the reason is because dot products are just made up of multiplication and addition. Multiplication and addition are commutative. That means the order can be switched and you'd still get the same answer. So since dot product is only made up of those two operations, dot product also is going to be commutative. So the fact that we can move things around and still get the same answer, that's called the commutative property. The way I remember that, I always used to get commutative and associative mixed up. So when you commute to work, you're actually going somewhere. Something's being moved. You are being moved from your home to your work. So commutative is when things get moved. Associative is just who is associated with who. There's parentheses in the associative property, and it's just who we have parentheses around that changes, but the order doesn't change.
There's like 4 of those: commutative, associative, distributive. Is there another one?
Identity.
Identity.
There's an identity property also. Okay, so it is commutative. The formula is really easy. It's just multiplication and addition. So next time we'll talk about why we do the dot product, because 15 has a meaning. Finds lots of different things, lots and lots and lots of different things. Now you might not do as much in physics as we're going to do with it in here. We might do more with it in here, a lot more. So we'll talk more about some theory next time.